Good afternoon, ladies and gentlemen, colleagues, attendees. We are beginning the panel session for the defense of the thesis by Mariia Dmitrenko. The thesis is submitted in conformity with the requirements for the academic degree of the candidate of science in chemistry. Specialization is 020004 physical chemistry. The topic: transport characteristics and physicochemical properties of membranes based on polyvinyl alcohol modified by polyhydroxylated fullerenes. By Rector's Order number 2701/1, as of the 9th of April 2018, I, Professor Lyudmila Yermakova, a Doctor of Science in Chemistry, Professor of the Department of Colloid Chemistry, PBU, was appointed Chair of the Dissertation Board. The members of the Dissertation Board are Andrei Ivanets, Doctor of Sciences in Chemistry, Deputy Director for Science and Research, Institute of General and Inorganic Chemistry of the National Academy of Sciences of Belarus. Vasily Lebedev, Doctor of Science in Physics and Mathematics, Head of the Laboratory for Neutron Research in Chemistry and Physics, Petersburg Nuclear Physics Institute, named after Konstantinov, of National Research Center Kurchatov Institute. Mikhail Goikhman, Doctor of Science in Chemistry, Leading Research Scientist, Institute of Macromolecular Compounds, Russian Academy of Sciences. Valery Tolstoy, Doctor of Science in Chemistry, Professor of the Department of Solid-State Chemistry, St. Petersburg State University. Under the federal law, as of the 23rd of May 2016, on amending Article 4 of the Federal Law on Science and State Scientific and Technical Policy, St. Petersburg University is entitled to confer its own academic degrees. The corresponding order number 6821/1 on the procedure of granting academic degrees at St. Petersburg State University was issued on the 1st of September 2016. According to this order, the panel discussion is valid, providing 2/3 of the appointed board members are present. The Dissertation Board consists of 5 people, 5 of which are present. Let me announce today's agenda. The discussion will not exceed 2 hours. Number 1, the chairman's presentation about the documents submitted by the candidate and their conformity with the requirements. Chairman's reply to questions at any 5 minutes. Number 2, the candidate's presentation with an overview of findings of the research, no more than 15 minutes. Number 3, questions to the candidate regarding the presentation, no more than 2 minutes per one question. The candidate's reply to the questions. Chair's overview of the submitted reports on the thesis and reports on the thesis, no more than 10 minutes per one person. The candidate's comments about the reports on the thesis. Then we have an open discussion, questions from the audience. The floor will be given to the non-board attendees. They can give a brief account of their ideas or ask a question, no more than 5 minutes per person. Those who are willing to participate should fill in the registration form and give their full name before they talk. Then we have the candidates' comments about the talks given by non-members of the board, no more than 5 minutes, and the presentation of the candidate's thesis supervisor. Then the discussion of the defense results and open balloting on the issue of conferring or non-conferring the academic degree. Then open balloting, vote counting, and recording the results in the minutes of the session. Deciding upon conferring or not conferring the academic degree, and candidate's closing speech. Before we proceed with the agenda, I kindly ask you to switch off your mobile phones. Our session is being broadcast, recorded, and interpreted into English. If there are no questions, let us begin. I'm sorry. First off, I have to list the documents submitted by Mariia Dmitrenko. The thesis by Mariia Dmitrenko was submitted in conformity with the requirements for the academic degree of the candidate of science in chemistry. The topic, transport characteristics and physicochemical properties of membranes based on the polyvinyl alcohol modified by polyhydroxylated fullerenes. It was approved for defense by the order of the SPBU Academic Secretary, number 2703/1, as of the 9th of April 2018. I have already introduced the board members to you. The candidate has submitted the following documents to the SPBU Academic Secretary. An application to Professor Nikolai Kropachev, Rector of SPBU, on the approval of the thesis for defense, submitted on the 5th of March 2018. Report of the Academic Supervisor, Candidate of Science in Chemistry, by Penikova Anastasia, Associate Professor of the Department of the Analytical Chemistry. List of published works containing 33 items. They are included in the Russian Science Citation Index. 5 works are published in peer-reviewed international journals. Letter of verification as of the 15th of July 2016, issued by St. Petersburg State University, which certifies that Mariia Dmitrenko was enrolled in a postgraduate course at St. Petersburg University from the 1st of September 2013 till the 15th of July 2016, specialization physical chemistry, and she passed 3 qualifying exams in history and philosophy of science. She got A4, foreign language, and physical chemistry, for which she got 5s. A notarized copy of the university diploma, number 09616 from St. Petersburg University, issued on the 4th of July 2013, given the qualification chemist. Thesis in Russian and English, a printed version with a manuscript copyright and a digital copy. The thesis formatting and reference list comply with the state standard R70. The above-mentioned documents comply with item 12 of section 3 of the order on granting academic degrees in St. Petersburg University. Appendix 1 to the order on granting academic degrees. Are there any questions that you might have about the documents submitted by the candidate? There are no questions. Thank you. Now, the floor is given to the candidate.
Good afternoon, members of the boards and the guests. The topic of my thesis is transport characteristics and physicochemical properties of membrane based on polyvinyl alcohol modified by polyhydroxylated fullerenes. Recently, membrane processes have been quite relevant for purification, concentration and separation of liquid mixtures. The development of chemical technology, which require membrane materials, require further development. And here the modification of known polymers by nanoparticles is quite relevant. The purpose of the thesis is to study the effect of the incorporation of fullerenol modifiers into PV matrix on physical, chemical and evaporation properties of the membranes. Here are the objectives of the thesis: to develop the modification methods of PVA by fullerenol, to study the structural and physical and chemical characteristics of polyvinyl alcohol fullerenol compositions, to choose the optimal fullerenol concentration and cross-linking method, and to study the transportation properties. We use PVA as a material because it has excellent physical and mechanical properties, and it is stable in most solvents, and it is also commercially accessible. However, its performance characteristics depend on the humidity because it is subject to molding in humid environment. To prevent molding, we use cross-linking of PVA by different methods, but usually toxic or cross-linking agents with low efficiency are used. Here we used polyhydroxylated fullerenes as cross-linking agents. These are soluble agents which allow us to develop an environment-friendly membrane. Besides, we can use this compound both as a modifier and as a cross-linking agent. The properties of mixed matrix membranes depend on the polymer solution and nanocomposites. We used dispersed fullerenol in an aqueous PVA solution. The characteristics of the membranes were studied with the help of dynamic light scattering. With the increase of the fullerenol concentration in the solution, we see the increase of the number of associates, which prove the formation of hydrogen bonds between PVA and fullerenol molecules. We form diffusion membranes by depositing the solutions on the petri dish with the further evaporation of the solvent. Since PVA is soluble in water, membranes based on PVA has to be cross-linked. So we used two cross-linking methods. Membranes were physically cross-linked. In other words, they were heated at 140 degrees Celsius for 100 minutes. And they were also chemically cross-linked by adding a cross-linking agent, maleic acid, and heating at 110 degrees for 120 minutes. To compare the characteristics, we also developed membranes which were not additionally treated. We proved the properties of the membranes by the spectral analysis. The structural changes must be reflected in the internal structure of the membranes, and to this end we used the scanning electron microscopy. Same method proved that the cross-section of different membranes have different morphology. Non-treated membranes based on fullerenol have lots of structural inhomogeneity. However, cross-linked membranes based on fullerenol have homogeneous cross-linking. To study the properties of polymer films, we measured contact angles using the sessile drop method. The contact angle becomes smaller if the content of fullerenol in the PVA matrix increases. It proves that the surface of membranes becomes more hydrophilic. Therefore, we can see the modification inside the membranes and also on the surface of the membranes. In order to prove the cross-linking of polymer chains, we studied the swelling degree of membranes in the water. The table demonstrates that the swelling degree becomes lower if the concentration of fullerenol increases, and this fact proves the cross-linking of polymer chains. Structural changes of the membranes will be reflected in the transportation properties of the membranes, which we used with the help of the evaporation process. Evaporation is a process of separating liquid mixtures. This method is environmentally safe for separating solutions. It is also characterized by low energy costs and high efficiency. It is possible to use this method to separate isotropic mixtures, as well as close boiling compounds and thermally unstable compounds. The procedure of evaporation experiment is shown on the slide. A membrane is inserted into the special evaporation cell, onto which a mixture for separation is poured. The liquid that has passed through the membrane permeate is removed as vapor from its backside and condenses on a trap cooled by liquid nitrogen. As modifiers, we used two types of fullerenes which have different OH groups. At the first stage, we studied the transportation properties of PVA membranes modified by the compound that you can see on the slide. Since this system has an isotropic point, it is difficult to separate the solution using traditional methods. However, evaporation with the use of hydrophilic membranes allows us to solve this task. PVA-based membranes and membranes using its composites were used to separate ethanol water solutions. The graph shows the dependence of the water content in the permeate on the water content in the original mixture for physically and chemically cross-linked membranes. Here you see that the concentration of permeate is different from the vapor-liquid equilibrium curve. PVA membranes, without being treated, can be used if the water content is less than 50%. However, membranes based on fullerenol are more stable and selective and can be used for solutions with different water content. So, chemically cross-linked membranes witness a high content of water, but for physically cross-linked membranes, the situation was reverse. When we studied the performance characteristics of the membranes, we also saw different trends. Physically cross-linked membranes had the lowest performance characteristics. However, chemically cross-linked membranes had the highest performance characteristics. These results are in line with the data provided by SEM. When comparing transport properties of the membranes, we found out that the best membranes to separate ethanol water solution is the one which is modified by 50% of fullerenol. At the second stage, we studied the transport characteristics of PVA membranes modified by the fullerene, which you can see on the web slide. This change of the compound was made because it is easier to produce. We proved that the properties of the two PVA membranes with different fullerenes are similar. Transportation properties of PVA C60OH12 membranes were studied for the evaporation of THF water and acetic acid water. This is explained by the fact that these compounds are commonly used as solvents, and for many industrial processes they have to be purified. During the evaporation separation, THF is used and water is a byproduct here. Besides, an isotropic mixture is formed. However, the acetic acid-water mixture does not have an isotropic point, but the volatility of water and acetic acid are close, which makes it more difficult to purify acetic acid by traditional methods. Evaporation separation can be highly effective if we use the right material for the membrane. And this is what was done in the thesis. Since the swelling degree of chemically linked membranes in acetic acid is quite high, the membranes can be destructed in case of a long contact with acetic acid. However, the degree in swelling is different, and it can lead to the selectivity of the membranes. But physically cross-linked membranes are stable to acetic acid, and they can be used for the dehydration of acetic acid. So, to separate THF water-soluble, we used chemically cross-linked membranes, and for the dehydration of acetic acid, we used physically cross-linked membranes. Here are the results that we received for the THF water separation. As you see on the slide, the results are shown on the graph. And here you can see the dependence for the PVA membrane and PVA fullerenol membrane. If the temperature is 30 degrees, then PVA fullerenol membrane is similar to the PVA membrane. However, if the temperature is 50 or 60 degrees, then the water contact in the permeate for the membrane with fullerenol is higher, but the performance characteristics are lower. The results show that fullerenol has a positive cross-linking effect, but the performance characteristics are not quite high to use for mass production. We can increase performance characteristics by making the membranes thinner. So we used and developed supported membranes, which consist of a selective layer which is deposited on a porous support made of polysulfonamide. The transport characteristics of the supported membranes and diffusion membranes were studied during the separation process of THF water. On the slide you can see the dependence of performance characteristics on the temperature for PVA membranes and PVA fullerenol membranes. The performance characteristics of supported membranes increased if the contact of fullerenol also increased, and the performance characteristics were much higher, and the permeate had a high content of water. So the best transport characteristics was attributed to the membrane modified by 5% fullerenol because it had good performance characteristics and high contact of water in the permeate. And this membrane can be used for industrial dehydration of THF. On this slide you can see the results for the separation of acetic acid water with the use of physically cross-linked membranes. Here, diffusion and supported membranes with a physically cross-linked layer based on PVA and fullerenol have been developed. The results of the separation of the acetic acid water are shown on the slide. Here the diffusion and supported membranes are shown. With the increase of fullerenol in PVA matrix, the performance characteristics become lower, however the water content becomes higher. The supported membranes allow us to increase performance characteristics by 6 to 9 times in comparison with diffusion membranes. However, there was a slight decrease of water content in the permeate. To increase the selectivity of membranes, we optimized the physical cross-linking by longer heating. So supported membranes based on PVA and on its composites were physically linked at 140 degrees Celsius for 420 minutes. The transport characteristics of the membranes were studied with the help of the evaporation of acetic acid water mixture. The table shows that with the increase of fullerenol, the water content in the permeate increases and performance characteristics become just slightly lower. Therefore, the best transport characteristics were attributed to the PVA-supported membrane modified by 5% fullerenol and physically linked at 140 degrees Celsius for 420 minutes. The transport characteristics were also studied during the evaporation process of a mixture which contained 30% of water. Since in real life the mixture may have a high content of water. On the slide you can see the line graphs which show the dependence and different characteristics. We compared the results with membrane PVA 1201 produced by Sulzer company. And here you see the dependence of characteristics and the water content in the permeate. Here you see that both membranes have high degree of selectivity. However, the water content in the permeate for the membrane that we developed increases a little bit in comparison with the original mixture. The performance characteristics is as follows. The performance characteristics of the membrane that we have developed is much higher than that of the PVA membrane if we separate weak mixtures. So, the membrane that we have developed can be efficiently used in industry for the dehydration of acetic acid. So we have come to the following conclusions, and you can see the main conclusions on the web slide. So we have developed new membranes based on PVA fullerenol composite. These membranes have better transport characteristics for evaporation dehydration. Are there any questions to the candidate? Who would like to ask a question about the presentation? I have a question. For example, if we take not acetic acid, but some other acid, how can the properties of membranes change? Since the mass transfer in evaporation can be described by the model diffusion solution, it consists of 3 stages. And here we see that sorption plays a major part. If we take a similar acid and get similar sorption characteristics of membranes, then we may expect similar separation. So you say that, for example, for carbonic acids it may work. Yes, that's what I say. Can I have a look at one of your slides? So here you see the structure of your membrane after the insertion of fullerenol. It is very similar to the compounds which are modified by aldehydes. Do you mean to say that these structural changes are due to the use of PVA and fullerenol? Is it possible that this structure can be really formed? Yes, we used spectral analysis to prove that this is the structure that was formed. If we speak about physically linked membranes where ether bonds are formed, we have seen the formation of ether bonds in our spectral analysis. And VMI method also showed the absence of peaked for physically cross-linked membranes, and it is characterized by OH groups in fullerenol. But what about the mixtures? Was it a water-soluble mixture? Fullerenol is water-soluble, then it is added to the aqueous mixture of PV and water, and then we made membranes out of this mixture. So did you have a chance to study the spectrum analysis? We use the spectral analysis for thin films because the used physical or chemical cross-linking methods, and we studied the membranes with spectral analysis. Please, I'd like to have a look at slide number 12. Here you see the change in the contact angle for chemically cross-linked membranes. At the same time, chemically cross-linked membranes are highly efficient. Can you comment on this dependency? In my opinion, it is connected with two major reasons. First of all, the addition of 5% fullerenol and the use of malic acid, in other words, chemical cross-linking, can lead to the structure being amorphous, and it increases the swelling degree. As a result, the performance characteristics also become higher. And fullerenol and malic acid also lead to the cross-linking of PVA chains, and as a result, the selectivity is also quite high. I think there's a controversy here. The cross-linking is higher, and the performance characteristics also become higher. This is explained by the fact that we use 5% fullerenol. We have shown that 5% fullerenol has an impact on the structure. It leads to a high degree of swelling, and it also leads to more homogeneous distribution of polymers in the structure. As a result, we have better transportation properties. Now, let's have a look at slide number 13. So in other types of treatment, we see the decrease of swelling, but in chemically cross-linked membranes, the situation is different. That's right. If we add less than 2% of fullerenol, then the swelling degree becomes lower, but 5% fullerenol increases swelling properties. And we used different methods to prove these structural changes. Are there any other questions? I have a question. So in your thesis, you have used lots of experimental data. How much time did it take you to obtain, well, one point when you speak about performance characteristics and so on? For example, at this slide, which shows the dependence. Thank you for your question. when we carried out the experiment, we wanted the weight of permeate to be not less than 0.3 grams. And we used the method of gas chromatography in this experiment. So with the increase of performance characteristics, we see the picture which is as follows. So chemically cross-linked membranes modified by 5% fullerenol were used, and the experiment took about an hour for 1 point. But we used several experiments to prove the value of performance characteristics. I have also another question. So you have the model on slide 10. This is a hypothetical model which shows what chemical bonds we might have there. Have you tried to build a 3D model, since you know the size of fullerenol? Is it possible that some micro pores might form there? And how fullerenol C60 and C70 influences the structure of the membrane? We didn't build any 3D models, but I would like to say that the introduction of fullerenol did not lead to the formation of any pores, and the SEM method proves this. Here you can see that sometimes agglomerates of fullerenol are formed on the cross-section, but there were no pores here. For the preparation process, we used non-porous membranes to separate mixtures with low moleculars. The transportation properties are due to the spaces between polymer chains. Probably there are some pores, but they are closed. And to prove this, I think you should have shown some other methods, but this is quite difficult since this is a carbonic material and it is difficult to find any pores there. I would like to ask you a question as well. When you speak about original membranes, how homogeneous were the membrane films? When we prepared the film of diffusion membranes, we used the width of 40 micrometers with a margin of error of 3 micrometers. What about the homogeneity of the film? Yes, we measured the homogeneity of the membranes. Was the width different? No, they're homogeneous in terms of their width. In most cases, the width was the same, so the membranes were quite homogeneous. So you poured liquid through membranes. You said that you poured liquid. Did you say so? Well, it's quite a difficult question. We poured some liquid, and during the diffusion process, something happens, because there is a discussion about the molecules. On the one side we see gas which is condensed, but on the other side we see water, so we don't know if it is water that passes through the membrane. Yes, you are right, we do not know the details of the process. So you prove the structure of the membrane using SEM methods. When your membranes are used in the evaporation process, they are swelled. How the structure of membranes are changed during this process, how the spaces between the polymer chains change, and so on. Yes, we conducted some experiments for swelling. Membranes were weighed at first, then they were put into water, and then we measured the changes in the swelling. Chemically and physically cross-linked membranes proved to be stable. They were stayed in water for 1 month and the structure did not change. Then we also studied the membranes by spectral methods, and we did not see any structural changes as well after the evaporation process. Yes, when membranes are stable, their structure does not change. But if we speak about water-soluble solutions, there might be some changes. How did you deposit the compound on the support? The support was fixed to a ring, then we deposited 2 layers and we dried it during 1 night until the dissolvent evaporated, and then we used physical or chemical cross-linking method, and that's how we got the membranes. Let's get back to slide number 12. So, how the change in the contact angle can be explained? I would like also to see the contact angle of the fullerenol, and I would also like to see on this slide the contact angle of the chemically linked membrane without fullerenol. Thank you for your question. When we introduced fullerenol in the PV matrix, we saw the cross-linking of polymer chains in a way that OH groups were transformed to the surface. As a result, the surface becomes hydrophilic and the contact angle becomes lower, since there are more OH groups on the surface of the membrane. Unfortunately, the contact angle for fullerenol film is not shown because fullerenol does not have good film forming properties, and it would have been quite difficult to create a fullerenol based film. Well, there are other methods of measuring contact angle, for example, using different powders. Thank you for your comment. We will take into account into our further research. The table shows that contact angles were measured for membranes with PVA and membranes with fullerenol, both chemical and physically cross-linked. When we add a cross-linking agent, we do not see any changes in the contact angle. So, fullerenol and the cross-linking agent do not make any difference. Please, let's have a look at slide number 18. The dependencies seem quite interesting. For physically cross-linked membranes, we see that with the increase of the modifier, we see the decrease of the performance characteristics. For chemically cross-linked membranes, the trend is reverse. Moreover, chemically linked membranes do not show the dependence of performance characteristics on the water content. So what's the difference between the different membranes, how the modifier impacts the performance characteristics, and how are performance characteristics different for chemically linked membranes in terms of the dependency. For physically linked membranes, we saw a trend in the decrease of performance characteristics with the increase of fullerenol, because they were treated at 140 degrees for 100 minutes and ether bonds were formed. Therefore, the use of fullerenol leads to a better cross-linking. However, in chemically cross-linked membranes, both ester and ether bonds are formed, and therefore the trend here is different. Yes, you are right. We do not see any proportionate dependence here. The increase of fullerenol leads to the increase of performance characteristics. But the differences are quite similar if we speak about 2% fullerenol. But the introduction of 5% fullerenol, which is a maximum concentration, leads to the increase of swelling degree, and it also leads to different lamellas, and as a result we have a high selectivity of membranes. So how are these dependencies consistent with the conclusion in your thesis? I mean conclusion number 1. As far as I understand, the type of cross-linking can lead to both increase and decrease of performance characteristics. Conclusion number 1 is a general one, but I would like to give an example of the separation of ethanol water solution. For physically cross-linked membranes, we see the decrease of performance characteristics if we introduce 5% fullerenol, but the graph shows that the water content in permeate depends on the introduction of fullerenol, and the membrane is stable. So among physically cross-linked membranes, the one which is modified by 1% of fullerenol has best transport characteristics. But for chemically cross-linked membranes, the one which has the best transport characteristics is the one which is modified by 5% fullerenol. And we also studied supported and diffusion membranes for acetic acid water and THF water mixtures. And we identified membranes with the best transport characteristics. For THF water solution, this is the one modified by 5% fullerenol, and for acetic acid water is the one which is modified by 5% and the one which is optimized by heating. As modified, you used one of the modifications of carbon. However, today there are different other modifications of carbon. So is it possible to say that we can use other carbon modifications to get membranes with better transport characteristics, and are you going to work in this area? Thank you for your question. You're right. As modifiers, different carbonic nanoparticles and modifications are used. But the most common one is the use of different cross-linking agents. They allow to cross-link polymer chains and to change the performance characteristics. For example, in one of the theoretical works, there is a description of a similar experiment. In this theoretical work, the membrane which was modified by cross-linking agents had very good transport characteristics, but our membranes still had better transport characteristics even than those described in the theoretical work I'm talking about. And on the last slide you can see the comparison of my membrane with the pore membrane, which is quite common and which is industrially produced. And if we compare our membranes with this membrane, then our membrane has better transportation properties. So we will develop our research even further. We will use the results to forecast the membrane properties and to test the separation of other mixtures. We have discussed the structures, and you know that fullerenol forms clusters in water solutions. 1222 is the one that you use. So you use cluster objects and chains for your system. How can you explain this from the point of view of getting the best properties? Could you repeat your question? How did you take into account the fact that fullerenol forms clusters in the solution? Does it have any impact on the qualities of your membranes? Is it the result of the clusters of fullerenol? We use the dynamic light scattering method to study the solutions. For fullerenol, for two types of particles were formed, 1.4 nanometers and 70 nanometers. In PVA fullerenol solutions, the size of the particles was also different, 93 and 138 nanometers. And to prove the fact that we did not have any associates of fullerenols, we started the solution with a similar content of fullerenol as the one which we found in the PVA fullerenol solution. Here we saw the associates with an increase of 70 nanometers. And if we see the size of the associates, whose size is 138 nanometers, then we see a different situation. I also have a question if you are not tired. Let's have a look at slide number 7. please tell me, your support that you used, does it have any membrane properties? Can it be used for the separation of mixtures? Yes, it is produced industrially, but it is not used for the evaporation, since it is porous and has a fixed size of pores. It is used for microfiltration, ultrafiltration, and so on. In this case, the porous support was used to provide mechanical support for the thin selective layer, and it did not have any impact on the qualities. You deal with films, and I think you should have used and you should have studied the qualities of the support as well. Maybe thermal and mechanical characteristics. We did not take these characteristics into account, but we know the characteristics of the support. Unfortunately, I cannot tell them from memory. But the characteristics of the support are known. Please, let's have a look at slide number 30. How can you explain the comparison here in the Pervac membrane? The original mixture changes, but the performance characteristics are not changed. I think that they use different cross-linking agents, but we do not know which, because they do not disclose the secret of their membranes. I think they use different cross-linking agents, and this Pervar membrane can be used to separate water solutions with up to 80% of water. I know this picture looks strange, but we have checked the results and have given you the average results of the dependence of performance characteristics on the water content in the permeate. Are there any other questions? I think we've had enough questions. You can take a seat. Since there are no external reports to the thesis, let's move on to reading out the internal reports. I'm going to read out my report.
I'll just focus on the critical remarks. It's not well substantiated why you use maleic acid as a cross-linking agent. The second is of a terminological nature. When talking about structural parameters of membranes, usually scores imply volumetric porosity, and polymer membranes, humidity, the size of pores or elementary cells when using a cell model of membrane description. Maybe the thickness of support or the selective layer, hydrodynamic or gas permeability, and other parameters. However, what you had in mind were only chemical bonds and characteristics between the components of the membrane material. The third critical remark. In the literature review, the major characteristics of evaporation are permeation, flux, and the separation factor. It's not clear why you don't focus in the experimental part of your research the separation factors for the new membranes that you developed. Apparently, and this is remark number 4, apparently the mixtures of the separation mixtures, these are those you focused on in your study. How can we use the results of your study to forecast the behavior and patterns of membranes when separating similar structured mixtures with similar physical and chemical properties. And one more remark is that the data set that you used is little used to calculate the characteristic of membranes. Here I mean theoretical conceptions of the mechanism of membrane transportation. Well, in general, the dissertation is written at a high level. The results were presented at different international and national conferences. The literature review is also relevant. For this reason, the Thesis by Mariia Dmitrenko complies with the major requirements set forth in order number 6821/1 as of the 1st of September 2016 on the procedure of granting academic degrees at St. Petersburg State University, and Mariia Dmitrenko can be awarded the academic degree of the Candidate of Science in Chemistry, specialization 020004 Physical Chemistry. Professor Evgenjevna, you're welcome with your report. We have no doubt that the dissertation we are discussing today is relevant. It focuses on a serious issue. It's the development of new materials and new membrane materials that are of huge practical interest, including the preparation, separation of different mixtures. For example, mixtures of organic matter with water. The results of the dissertation are accurate. For example, we have new PVA polyhydroxylated fullerene membranes. These are organomineral membranes that can be used in preparation of water organic mixtures. Cross-linking, physical and chemical cross-linking conditions are well defined. The candidate has shown physical and chemical properties and transport characteristics and how they affect selectivity to the desired component of the new membranes. The candidate has used quite a range of approved methods in her study. There are some minor critical remarks I can make. And on figure 21, we see dependence of the water content in the PMate on water content in feed. However, this doesn't allow to make any conclusions because of the proximity of values of all the membranes in question. The calculation of activation energy for diffusion and supporting membranes is made out of linear dependence of L and J on temperature. It's plotted on 3 points. I doubt accuracy and relevance of this kind of calculation. You should have added 2 more points with interim temperatures. However, the critical remarks I have made does not anyhow affect the general high opinion that I have of the dissertation. So Mariia Dmitrenko can be awarded the academic degree of the Candidate of Science in Chemistry. Her thesis complies with the major requirements set forth in order 6821/1, and she can be awarded the academic degree, specialization 020004 Physical Chemistry.
Диссертации даже Мария Евгеньевна.
We understand that the thesis is quite relevant, and the author of the thesis studied the issue. I think this is one of the best theses in the area of creating fullerenol-based membranes. And I also like the fact that the results can have some usage for atomic energy. So in general, I see practical significance of the thesis, and she has received fundamental results, and the research findings can be implemented in various areas. So the relevance and practical significance are out of the question. If we speak about the quality, we can say that this is a serious, complete research work. The credibility and the validity of the results are proved with the help of various methods, and this is the merit of the thesis. The research findings to be defended are proved and justified, and I liked that she used different methods: cross-linking, the optimization of the membrane content, and she also obtained membranes that can be further industrially manufactured. We know that the thesis has an international significance. She has presented her research findings at different Russian and international conferences, and the volume of the thesis is also quite large. So this is a research graduation work. She analyzes the theoretical sources, and all the 3 chapters are written in an interesting and elegant language, and all the research findings are also well written. Now I would like to speak about some critical remarks that I have. Page 55, dynamic light scattering data. For PVA fullerenol membranes, we have found 2 sizes of particles, but you do not speak about the share of polymers and fullerenols that form the associates. Figure 18 shows us the crystallinity degree. You do not show the decomposition process, and you do not say how the introduction of fullerenol influences the packaging of chains. And number 3, at page 104, you speak about the activation energy values. We have found the sharp decrease of the value for supported membranes, which can be explained by the decrease of crystallinity areas. However, the change is 54 or 42%. So how can you explain the decrease of the activation energy value? There are some misprints, but I'm not going to talk about them. So the critical remarks do not change my positive evaluation of the thesis. The research findings and the assumptions are well justified, and the thesis contributes to the development of physical chemistry, molecular chemistry, and the chemistry of polymers. The research findings can be used in different research institutions, and the thesis by Mariia Dmitrenko, transport characteristics and physicochemical properties of membranes based on polyvinyl alcohol modified by polyhydroxylated fullerenes, complies with the major requirements set forth in the appropriate order, and Mariia Dmitrenko can be awarded the academic degree of the candidate of science and chemistry, specialization 020004, physical chemistry. The floor is given to Professor Goichman. I'm not going to read out my report from beginning to end because it's quite long and it has all the necessary components. However, I would like to say that recently we have seen a lot of efforts in the area of forming PVA-based membranes, because such membranes can be cheap and environmentally safe. And in the thesis, we see one of the best attempts in the area. So the relevance of the thesis is connected with the development of new approaches to developing effective membranes based on PVA. The methods of creating membranes by using physical and chemical cross-linking, as well as methods of making supported membranes, open up new possibilities for separating mixtures in order to obtain different important components. And this is the practical significance of the thesis. The scientific novelty is that here PVA fullerenes composite cross-linked by two methods are compared. And with the help of spectral methods, we have seen the structural characteristics of the membranes. So, in general, the thesis uses lots of experimental data, and it is done at a high scientific level. She has demonstrated her ability to carry out serious scientific research and her ability to analyze chemical dependencies in interpreting scientific results. The research findings allowed her to carry out a complete and thorough research. However, I have some critical remarks. While studying the thermal stability of the membranes, the lower stability of chemically cross-linked membranes can be explained by the fact that physically linked membranes have double carbon bonds, which increases their stability. As for the thermal stability of membranes cured by maleic acid, this can be attributed to the low degree of crystallinity. However, these statements are quite controversial, since most linked polymers are amorphous compounds, but their thermal stability is higher than that of their linear analogues. And the double bonds can lead to the decrease of heat resistance and not to the decrease of thermal resistance. Number two, you did not justify the use of maleic acid as a cross-linking agent, since double bonds of maleic acid are not used. As a cross-linking agent, you could have used any aliphatic carboxylate acid. However, the critical remarks do not downgrade the research. The thesis is relevant and has scientific novelty, and all the research findings are justified and they seem credible. So I believe that the thesis by Mariia Dmitrenko, Transport Characteristics and Physicochemical Properties of Membranes based on PVA modified by polyhydroxylated fullerenes, complies with the major requirements set forth in the order on the procedure of granting academic degrees at St. Petersburg State University. And Mariia Dmitrenko can be awarded the academic degree of the candidate of Science and Chemistry, specialization 020004, Physical Chemistry. Thank you.
I'd like to focus first on the accuracy of the results. The topic the candidate focused on has been developed in the recent 20 years. it allows to solve a number of challenges. They say isotropic mixtures can be separated by evaporation without the use of the third component. We should have to consider that a membrane is actually a third component. So it's more effective to use a membrane as a third component than some chemical substance. So let me underscore once again that this topic is in line with the major scientific efforts these days. So the candidate focuses on the physical and chemical properties of the new technology. The candidate focuses on quite a number of important parameters, such as crystallinity, morphology, swelling degree, and thermal properties. Well, turning to the critical remarks, the study would benefit if the candidate had focused more on the way fullerenes were obtained. She doesn't focus on that at all. She only writes that fullerene was obtained at the Department of the Chemistry of Solids of the Institute of Chemistry at St. Petersburg State University. It complicates the perception of your dissertation. Maybe this is something that you should consider in future. There are some minor inaccuracies, some X line and Y lines lack titles. Sometimes you fail to give dimensionality. There are some misprints. Let's leave them aside. I have listed all the pages. The dissertation is logical and well structured, is written in clear language, except for a couple of sections where you focus on describing the experimental data and the description of spectra. Oh, there is no doubt that the thesis by Mariia Dmitrenko complies with the major requirements of St. Petersburg State University to defenses of candidates' dissertations, and there is no doubt that Mariia Dmitrenko can be awarded the academic degree of the Candidate of Science in Chemistry, Specialization 02-0004 Physical Chemistry. I would also add Chemical Sciences. I'd like to thank all the members of the dissertation board for all the critical remarks. I would like to say that I accept all the critical remarks that you've made, and I'd like to answer a few questions that you had in your reports. Talking about the proximity of dependencies of the concentration of water in permeate on the concentration of water in the input mixture allows to conclude that fullerene modified membranes have high susceptibility to water, as this dependence of permeate input mixture for evaporation process is critically different of the equilibrium curve of vapor and water in the system ethanol water, which shows that this process was effective. I accept your remark about the accuracy of the calculation of energy activation. However, this linear dependence of the logarithm on the flux on reciprocal temperature allows to say that this dependence is governed by the Arrhenius equation, which shows that the results are accurate. fullerenol was obtained in heterogeneous conditions with the interface catalyzer of hydroxide tetrabutylammonium from fullerene C60, whereas fullerenol C6012 was obtained by hydrolysis of bromine, bromine-derived fullerene in the presence of alkali. Talking about IR spectroscopy, I'd like to say that the thickness of films was no less than 5 microns. When fullerenol is introduced into PVA membrane, it affects a number of peaks, which refer to OH groups, ester bonds and ether bonds, and this analysis is found in the dissertation. I used a vacuum pump, Gidromech 2B 1.1. Its effectiveness is 1.1 liter per second, and the pressure on the membrane was 2.0 Pascal. When analyzing solutions by the method of dynamic light scattering, we only had associates for PVA fullerenol solutions. The degree of polymer and fullerenol in the associates was only 1%. Talking about the crystallinity, I really would like to thank you for this critical remark. The maximum peaks were within the experimental marginal error. They didn't anyhow affect the packaging of chains. When comparing the energy activation data for supported and diffusion members, there is a huge difference in data when fullerenol is introduced. Activation energy is smaller by 7 kilojoules by mole for diffusion membranes. It happens when 5% fullerenol is introduced, and for supported membranes it happens when 1% fullerenol is introduced, which means fullerenol decreases activation barrier. This data allows to conclude that this effect is really strong when thin selective layer of a supported membrane is being formed, because the hydrophobia balance changes because of the formation of polar groups and changes in crystallinity. So the thin layer of membranes swells, and these decreases activation barrier. Why did I choose maleic acid as a cross-linking agent? When creating chemically cross-linked membranes, I use different linking agents such as glutaric aldehyde, mixture of sodium hydroxide and sulfuric acid. Maleic acid has optimal transport parameters. However, if we use the popular glutaric aldehyde, this required the use of concentrated hydrochloric acid, which decreased the flux. If sulfuric acid was introduced, then mechanical properties of PVA membranes got worse. Maleic acid can form ester bonds, and when PVA membranes are modified, some carboxy groups can remain, and this might affect transport characteristics of PVA membranes cross-linked by maleic acid. Transport characteristics of modified membranes were given as formation flux and separation. In Chapter 3, selective parameters of membranes were given as the content of water in permeate, so that to compare the concentration dependence of permeate input mixture and the equilibrium curve of liquid vapor to evaluate effectiveness of evaporation separation. Mass transfer during evaporation can be described by a model dilution diffusion, which comprises two stages: selective sorption, diffusion, desorption. Sorption is crucial. We can forecast similar separation if we use similar membranes with similar sorption parameters. The dataset we have gathered will be used to calculate different membrane parameters in our future study. I accept the remark about thermal stability of the membranes I designed. The dispute here is because of the inaccuracy I had in the thesis when I described them. Chemically cross-linked membranes had lower thermal characteristics as compared to physically cross-linked membranes. The range is from 170 to 370 degrees Celsius. Steric bonds provide less loss of mass. The analysis of scholarly works showed, here I mean one work by Professor Konstantinos Dissertation, he modifies PVA membranes by carbon nanotubes. So the data on crystallinity was taken from scholarly works by colleagues. As I have already said, maleic acid was used to achieve the desired level of transport characteristics. When other acids are used, then PVA chains are cross-linked at a deeper level, which affects the transport properties of membranes. Thank you very much. Are you satisfied with the answers? Is there anyone present here would like to participate in the discussion? You're welcome. My name is already on the list. You can use the podium microphone. Mrs. Chairwoman, members of the Dissertation Board, colleagues, I have read the thesis completely. Could you please introduce yourself? Sergei Yermakov, Professor on the Institute of Chemistry, St. Petersburg State University. I have read the thesis from cover to cover. And what I find the most exciting about this research, is that it provides a good experimental basis. To some extent, it's a bit too theoretical, yet it is combined with a huge practical effort that the candidate made. This study is what modern science really needs. When we have research in technology, so if we have a research that allows to increase the performance of some 2, then even this minor increase might have global positive consequences, which are difficult to overestimate. This study can find wide practical application. The results of the study are published in established international journals in the area, which is another proof of the relevance of this study. So what I would like to say is that Mariia Dmitrenko can be awarded the desired degree. Good luck and thank you. Is there anyone else willing to take the floor? No? Thank you. As we didn't hear any critical remarks, then the floor is given to the academic advisor of Mariia Dmitrenko. Good afternoon, ladies and gentlemen, colleagues, members of the Dissertation Board. I have little time to talk about Mariia Dmitrenko. I try to be brief. It is the only person I'm giving the third report about, because she wrote her bachelor graduation paper and her master's thesis under my supervision. She joined my team after she had participated in 2 different research teams, so it was her conscious choice to choose a place where it would be interesting for her to work in. She studied all the methods and she never missed any training on any equipment that the lab has. Actually, Mariia didn't intend to enroll on a postgraduate course, but then she changed her mind. She remained within our team, which really made us happy. She is an independent scholar and independent thinker. She was already well qualified to use certain methods after her bachelor studies. She went on an internship to France. Masha was invited to go to France on a postdoctoral program, but I hope that doesn't really come true because we want her to stay with our team. She is a member of numerous grant programs. She has worked with different kinds of polymers. She publishes the results of her research works in high-impact international journals and participates in international conferences. She became #1 in St. Petersburg competition in chemistry. Mariia Dmitrenko is an assistant professor of the Institute of Chemistry. She is the only person who could take this position without having a degree. She applied for this position and won the competition. She is an independent scholar and really a professional one. I hope she continues to work with us in our team. Mariia Dmitrenko has shown her best today. She's fully aware of her material. Now we're going to discuss the results of the defense. Could everyone present leave the auditorium and switch off the broadcast?
Продолжим наше...
Let's proceed with our agenda. Please switch on the broadcast. We are now starting the open voting on the issue of conferring or non-conferring the academic degree. So I put to the vote the issue of conferring the academic degree in conformity with item 23 of the order granting academic degrees at St. Petersburg State University. Let me remind you that the decision of the Dissertation Board on conferring the academic degree is positive, provided it has received 50% of the votes from no fewer than 3 members of the Dissertation Board. I have thoroughly studied the thesis. I have carefully listened to the presentation Mariia Dmitrenko made today. So it raises no doubt that Mariia Dmitrenko is a thoughtful scholar. This thesis is a complete study. Many results were published in high-impact international journals, and the candidate can be awarded the academic degree. Professor Lebedev, what do you think? I think the candidate can be awarded the academic degree of the candidate of science and chemistry in physical chemistry because her thesis complies with all the necessary requirements. At all the levels of her research, she was active and independent as a scholar. I'm voting for conferring the academic degree. Mr. Goifman, dear colleagues, my opinion is not an exception. We have listened to an interesting presentation today. The candidate is fully aware of all the theoretical and practical material of her dissertation. She can really be awarded the academic degree. I'm voting for. Professor Tolstoy, your opinion. Let me highlight that the study by Dmitrenko complies with all the requirements and has all the characteristics of the studies of this level. I would like to vote for. The results of the study are well presented, and I've checked it on purpose. Her academic papers are already cited by other leading scholars worldwide, including one Nobel Prize winner. So the research is accepted on a global level. This defense is being conducted according to the new SPBU rules. I can draw a comparison. It might be incorrect, maybe, but yet. The requirements set forth to candidate dissertations at St. Petersburg State University are higher than in other universities. For example, for scholarly works published in international journals is a very stringent requirement, I suppose. 5 specialists in the field have to thoroughly study the dissertation, which also impacts the level of the dissertation. So once again, I'm voting for. Let me share my opinion. Mariia Dmitrenko has produced a very positive impression on everyone present here. She is really fully aware of all the experimental, practical and theoretical material of the study. So, colleagues, attendees, ladies and gentlemen, let me announce that 5 out of the 5 board members have voted for conferring the academic degree to the candidate. So Mariia Dmitrenko can be awarded the academic degree of the candidate of science and chemistry, specialization 020004. You're welcome for the closing speech. I would like to thank you, Mrs. Chairwoman, for the session. I'd like to thank all the members of the Dissertation Board for the interest that you showed to my research, for the time you took to read it, for the reports. I'd like to thank my academic advisor, Anastasia Penikova, for the contribution she made into this defense. I'd like to thank my colleagues for their support and help, their moral support on the way to this day. I'd like to thank the head of the department I work at, Professor Yermakov, for his time, for his patience and understanding. I'd like to thank the staff of the resource centers of St. Petersburg State Universities who helped me with measurements for my dissertation, for the training in different research methods, for their help in the experiments I conducted, for the love and support of my mom as well. Thank you very much, everyone. Colleagues, thank you. The session is over.